Hello everyone, we are Team7. I'm Chen Zhengwei. Our topic is joint image restoration and compression via prompting. And here is our outline. First, we will introduce our relative work, then we'll present our project proposal. And next page. Next page. Before we present our final proposal, we have to briefly introduce two sections, compression and prompt. First of all, compression is a method to reduce the redundancy within the transmitted data and hope that the compressed data can be reconstructed well and just need to send a few bitstream for faster transmission. Second, prompt is a technique that uses a small set of learnable parameters as the conditioning signal to guide the model to fit different task-specific adaptations. Here I'm going to talk about image compression only. In the learning-based image compression field, the most common architecture is using variational autoencoders as the compression model. Then the following is the first paper which proposed a hyperprior BAE based for learned image compression. To date, it's still a widely used architecture in the compression field. They incorporate a hyperprior to efficiently capture spatial dependencies to estimate the posterior for the prior. First, the input image will go through the main encoder to generate the lantern representation for compression and transmission. Then hyperprior will predict the probability for each element within the lantern representation and estimate the accurate B-rate of the bitstream for compression. The assumption here is that the distribution of lantern representation is Gaussian distribution. So the goal of hyperprior is to predict the scale value for Gaussian in this paper. But in the recent research, hyperprior will predict both mean and scale for bitrate estimation. Finally, the compressed lantern code will be reconstructed to the output image called reconstruction here. In the training process, they advise to add the uniform noise in training for more stable training. Additionally, the prior needs to be flexible enough to assume the shape of the posterior, a unit weight uniform density. Due to its infinitely steep edge, the uniform distribution is corner case for not only the Gaussian density model, but also the non-parametric model. To fix this, we incorporate the added noise directly in the prior and hyperprior by convolving the underlying density model P with the standard uniform noise. Then I would like to talk about the loss function of the compression task. The left-down figure is a brief overall architecture. In variational inference, the goal is to approximate the true posterior P y tilde z tilde given x, which is assumed intractable with a parametric variational density Q of y tilde z tilde given x by minimizing the expectation of layer K divergence over the data distribution P of x. Then the formula can be simplified to the right-hand side. The first term is 0 since Q is a product of uniform densities of unit width. The second term, it means the likelihood is the distortion, which is to measure the difference between the original image and reconstructed image. The third and fourth terms represent the cross entropies encoding y tilde and z tilde, respectively, which is the bitrate of the transmitted lantern code. This loss is the trade-off between distortion term and rate term. Goal is to compress the bitrate as much as possible, and the reconstructed quality can be good as well.
Okay, now I'm going to talking about the prompt tuning, how the prompt tuning adapt the image. So let's briefly introduce the prompt tuning. Prompt tuning is a concept borrowed from neural network processing, or NLP model. And NLP models are often very large. Fine-tune all parameters for a specific test is hard and almost impossible. So prompt tuning introduces a small set of learnable parameters called prompt for test-specific adaptations. This approach uses just 1% of learnable parameters, can match or even outperform fine-tune. The difference between prompt tuning and a proposed method is that in our method, we will fix the main network and only train the prompt part, instead of training all of the parameters. And here is a method inspired by visual prompt tuning (VPT) in previous slide, called TIC. This figure the figure here is VPT and TIC. In the left-hand side, illustration of is an illustration of the VPT. The transformer-based feature extractor is frozen, and only trainable parameter is a test-specific prompt, which is the TS prompt. And then the right-hand side is an illustration of the TIC. The paper took an image compression codec and added some instance-specific prompt in the encoder and a test-specific prompt in the decoder to adapt the model to utilize for machine perception task. And of course, the transformer codec is frozen, only the prompt is trainable. TIC is primarily for human visualization, while TIC can adapt it to other downstream tasks. And here is the overall architecture of the TIC. The blue and gray block is a common use framework for end-to-end learnable image compression, which is referred to a pre-trained codec in this paper. Notably, it follows a variational autoencoder VAE-like framework. The codec is driven from a model in 2021's paper called Transformer-Based Image Compression. The codec employs the swing transformer block as a basic building block. We can see that the STB represents the swing transformer block, and also in this architecture, it incorporates convolutional to adjust feature resolution. We can see that the convolution layer in the encoder is struck 2, so having the feature resolution. By contrast, the convolution in the decoder side will upsample a feature, which is a double. And here is the main codec with the encoder and the decoder. And here is a hyperparameter. Here is a hyperparameter encoder and hyper decoder to predict the distribution of the image feature. And the last part is the main proposal of the TIC. The purple part up there is an instance-specific prompt, which uses input image X as a condition to adapt the image feature. And the orange part down there is a test-specific prompt, which adds some learnable parameter. The parameter do not related to the input image, only related to a task. And here we'll quickly go through the codec swing transformer block, STB block. And here is how we insert the prompt into it. The figure on the slide is a normal swing transformer block, which take an image feature as an input and following by multi-head self-attention. And then we insert the prompt to the image feature before going into a STB block. The prompt is generated by prompt generation network, and it also contain image information, which makes our codec content adaptive. And here is a training objective of the TIC. The loss here contains two parts, rate and distortion. The first rate represents the bit rate per pixel. It is a measurement of how many bit bandwidth during the transmission. And the second is distortion. In the compression codec, normally compares the difference between the output and input image. Since TIC current goal is to transform towards machine perception, The distortion here is a perceptual loss of the downstream recognition model.
Okay, so here is our project proposal. In our term project, we want to focus on denoising task, which is one of the image restoration tasks, and we hope to integrate it with a compression model. Our primary goal is to perform image denoising and decoding simultaneously during the image transmission process. Inspired by the previous paper TransTIC, we plan to transfer a well-trained transformer-based image codec, in this case TIC, to denoising task by injecting prompt on the decoder side. Originally, if someone wants to do denoising in a compression system, the most intuitive way is to connect a model after the compression model. However, this led to increased model size and complexity. So our goal is to integrate denoising functionality into the decoder itself, rather than adding an extra denoising model afterward. Okay, so our strategy involves incorporating prompts into the compression decoder within TIC. This transforms TIC from a pure compression model to a compression model enhanced with denoising capabilities. Therefore, our approach achieves dual functionality, integrating both denoising and compression within a single model framework. In our expected method, we will incorporate these prompts in two different ways. For the first one, we are going to add task-specific prompt to the decoder, as shown in this picture. And next, for the second way, we will add an instance-specific prompt generator to the model. The input to the instance-specific prompt generator is the compressed lantern. It is to adapt the image feature according to the input image. And the benefit and uniqueness of our proposed system and the plug-in prompt mechanism on decoder side is that it has the flexibility to switch between standard image reconstruction and denoising reconstruction from a single compressed bitstream. To put it simply, when transmitting a single compressed bitstream to the receiver, user can have the option to reconstruct either the original image or a denoised version according to their preference. And these two decoder in the green box is the same model. When user wants to obtain a denoised version of the image, the only requirement is to insert this prompt during the decoding process. On the other hand, if the user wishes to acquire the original image, they can simply use the original decoder to reconstruct the image. And ultimately, this approach leads to the realization of single bitstream serving multiple tasks. And this diagram illustrates the model's architecture of our first expected method. We adapt a pre-trained codec for the standard image reconstruction task. By freezing this pre-trained base codec, which is in these blue boxes, and we then train the task-specific prompt in red boxes on the decoder side for image denoising task. And as mentioned before, these task-specific prompts are some learnable parameters and are not related to the input image, but only related to the task. Our second method replace the task-specific prompt with instance-specific prompt and show in this purple part. And this task-specific prompt use compressed lantern Y head as condition to adapt the image feature. And in the experiment section, we plan to implement the two methods mentioned in the previous slide. They are denoted as variant 1 and 2 in this table. These variants involve injecting TP type and IP type prompts separately on the decoder side. And the subsequent variant 3 to 5 are the method we aim to compare. The first is the original TIC model without any prompting technique, and this serves as our baseline. The second involves adding an additional denoising model after the compressed model. And the third is the trans TIC model. And following Restoma, we plan to perform this denoising experiment on synthetic benchmark dataset generated with additive white Gaussian noise. We will add white Gaussian noise to this high-resolution image dataset to generate our synthetic training and testing dataset. After training process, we will compare the denoising performance of our method with these three comparative methods as mentioned in the previous table using the PSNR matrix. And that's all of our proposal test presentation.